chapter 18 today. Thursday, we're going to have a review on this material. And we'll have the lab number 5 on formation constant of complex ion. So be sure your lab notebooks are prepared. And that's the last lab that we're going to do. Now, when will that report be due? That'll be due on Thursday, the 24th of July. So that'll be 1 week later. And in fact, we'll have exam on this material a week from today, next Tuesday. And then we'll start Thursday will be a final exam review. And if we need it, we'll finish the review on the 29th of July. Otherwise, if we get through all the material for the final exam review on the 24th, that Thursday, then we can have the final exam on Tuesday or Thursday. I've got it listed on Thursday, but we just assume that's a deadline. But you can take it on Tuesday if we finish the review on the previous Thursday. All right. So let's cover electrochemistry. That's chapter 18. And get those as far out of the way as possible. All right. Electrochemistry is the study of the change of chemical to electrical energy, or vice versa. Right, you can go both directions. It is reversible. And we're going to find out how you can reverse the interchange from chemical to electrical energy is easy. That's a battery. The other direction, electrical energy to chemical energy, is electrolysis. And we'll cover both of those topics today. First, we need to get a handle on oxidation reduction. And I can't recall if we've covered this or not. Maybe in when we looked at different types of chemical reactions, we introduced oxidation reduction. But it bears repeating. We abbreviate that redox, just because it sounds better. Oxidation and reduction. Remember, oxidation is the loss of electrons. Reduction is the gain of electrons. And there's our mnemonic, if I haven't already shown that to you. Oil rig. So oxidation is loss. Reduction is gain of electrons. And that's true no matter what the situation, whether it's a battery or whether you're proceeding with an electrolytic process. Oxidation is always loss of electrons by something. Okay, let me go to the next slide and cover reducing agent and oxidizing agent. No, it's not going to do that. All right, so let's say we have how about this one? Sodium and chlorine gas. That's going to produce table salt. But we need 2 here for 2 chlorines and 2 here for 2 sodiums. So now we have a balanced equation. If we go from sodium to sodium chloride, sodium had to lose an electron. In other words, electron had to be transferred to chlorine. In fact, 2 of them had to be. And that makes sodium is oxidized. And chlorine is reduced. Notice that you can't have one without the other. If there's an oxidation, there has to be a reduction somewhere in that reaction environment. And the other terminology that we use is if sodium is oxidized, it causes the reduction of chlorine. So that makes it the reducing agent. And vice versa. If chlorine is reduced, it causes sodium to be oxidized. Okay. Now, those are qualitative expressions. We're going to learn how to quantitatively track electron movement. And to do that, we need a concept called oxidation states. What we mean by that is the species that we're looking at neutral? Does it have a perfect balance of electrons and protons? Does it have an excess of electrons, or does it have a deficiency of electrons? And we need a way to bookkeep in order to track those electrons. There's Jada. And that's what we're going to do with these rules for oxidation states. All right, I'm not going to write them on the board because I've got them here on these slides. If we have an atom, freestanding atom, in any reaction equation, and it doesn't show any kind of charge, it's just there, it's either in its most stable state. So in our case, sodium would be just a single atom of sodium solid. Chlorine, its most stable is diatomic. So Cl2 would be its most stable state at 1 atmosphere pressure and room temperature. And its oxidation state for each of the atoms in that chlorine is 0. If we have a monoatomic ion, say we put sodium chloride in solution, and we have sodium ions and chloride ions, the oxidation state of each one of those ions is the charge. So sodium would be +1, chlorine would be -1. If we have oxygen, now we have to set up these rules because we can't make rules for every element. So we establish rules for some of the elements, just enough of them, so that if we find them in a compound, we can calculate the oxidation state for the remainder. So if we find oxygen in a covalent compound, we give it a -2 oxidation state, with one exception. Anytime you have a peroxide of any kind, and say we have some group over here and some group over here, these could be hydrogens for hydrogen peroxide, or they could be any other type of peroxide if these were carbon extensions. Or if we have a percarboxylic acid, which is the last one in that list, where instead of this, right, instead of that, we have COOOH. Right? Okay, in that case, when we have two oxygens hooked together in a covalent compound, each oxygen is -1, and the pair is -2. All right. Hydrogen. In a covalent compound, we give hydrogen +1. For instance, if we have water, like that. Oxygen would be -2, correct? Hydrogen would be +1, +1. That way they balance, right? Two pluses balance a -2. That's a neutral compound, and we know water is neutral. In ionic compounds, where hydrogen is the second atom, our example there is aluminum hydride. Whenever you have a metal in a compound, it always assumes the positive charge. So that means that hydrogen has to be negative. It can be nothing else. Then we can balance with 3 minuses and a 3 plus. Fluorine. Come on. There we go. Fluorine, the first of the halogens, is always -1. Whether it's covalent or ionic, doesn't matter. It's always -1. No exceptions. Now the other halogens can have various charges. The sum of the oxidation states for a neutral compound is 0, just like water. We showed you with water. Any other compound that does not have a charge, and in fact, if it has a charge, it's a polyatomic ion. And that's probably the next rule. For polyatomic ions, the sum of the oxidation states for all of the atoms must equal the charge on the polyatomic ion. So, for instance, let's back up. For instance, if we have carbonate, like that, okay, we know from our rules that oxygen is -2. So a -2 times a 3 is a -6, right? What would carbon have to be in order to preserve a -2 charge? It would have to be a +4. So a +4 and a -6 is a -2. Alkali metals are always +1. Alkaline earths are always +2. You may recall these rules from nomenclature, right? When we had type 1 compounds, where the metal is a fixed charge. So we're borrowing from that concept. Alkaline metals are always +1. Next door neighbors, alkaline earths, are always +2. We left one out, actually. And it comes from nomenclature also. Aluminum is always +3. Gallium and indium, they're always +3. Okay. When chlorine or nitrogen are present, now we said that, back up, fluorine in a compound is always -1. Chlorine can vary. The pnictogens can vary. Nitrogen, phosphorus, arsenic, antimony. They can vary. But if push comes to shove and we find nitrogen or chlorine in a compound and it's paired with an atom for which we don't have a rule, then we give them a -1 charge for chlorine and a -3 charge for nitrogen. Otherwise, we're stuck. Like for cyanide, right? What do you do with cyanide? We don't have a rule for either carbon or nitrogen so far. So we pick the more electronegative one, right? One to the farthest right, and that's on -3. That means we need to preserve one of those minuses. That means carbon has to be +2. That's the only way we can get ourselves out of that corner we painted ourselves into. All right, so here's some examples. Let's see, who else is showing up late? Or was it, oh, there's Ada. Let's see. Madison and Ann, we're still missing. All right, for these examples, if we have potassium dichromate, let's see what I'm doing. Potassium, excuse me, I went backwards. Potassium dichromate. We have rules for oxygen and for potassium, right? Alkaline metals are always +1. Oxygen is -2. So we add up the total negatives for oxygen, -14, right? 7 times 2. And this is only 1. 2 times 1 is +2. So together, these are -12. Lift out. There. So -12, since this is a neutral compound, -12 has to be balanced by positives from chromium. So together, chromium has to be +12. But we've got 2 of them. So each one is a +6. All right. That's how it's done. We already did carbonate. I think we did carbonate. Yeah. Manganese dioxide. Should be able to do that one in our head. Right? Oxygen is a -2 times 2 is a -4, so manganese has to be a +4. Right? PCl5, here's the one. Here's one where we're stuck if we don't assume that chlorine has a -1 oxidation state. -5 total, +5 for phosphorus. Okay. Sulfur tetrafluoride, we have a rule for that one. -1 here. That means -4 here, +4 there. Okay. Practice, practice, practice. Calculating these oxidation states should become second nature to you. Keep practicing until you feel comfortable calculating these oxidation states. Because this is only the first step. We're going to use these oxidation states to help us track the movement of electrons, and in the first case, how to balance equations using their oxidation states. All right. Speaking of balancing equations, when I mentioned oxidation always accompanies reduction. Since that's the case, we can split an equation into 2 half reactions. And one of the half reactions expresses reduction, the other half reaction expresses oxidation. And this is just an example. We're gonna take one from the ground level and work our way through half reaction balancing. But this is what it would look like if we had split this equation into reduction step and oxidation step. Notice that the reduction step, electrons are on the left-hand side because they're being added to the manganate ion, right? That's reduction. We're gaining electrons into the manganate to produce products. Whereas the oxidation, the electrons are on the product side because the iron 2+ has lost electrons to produce iron 3+. Notice also, we could add these equations back together because they are balanced in terms of their electrons. The electrons gained equals the electrons lost. Once that occurs, and you follow the procedure, then you can recombine these equations and produce the overall expression above. One other thing you'll notice is when we write oxidation reduction reactions, sometimes we leave out the spectator ions, right? That iron that we put in the reaction mixture probably has a counter anion to go with it, like chloride. And the manganate ion probably has a counter cation, I don't know, like potassium. We just leave those out because they don't undergo any type of oxidation reduction. So it's kind of like a net equation, a net ionic equation that we're dealing with. All right. These are the steps for balancing an equation using the half reaction method. Remember in the first semester, we balanced equations by my budget method. Some of these oxidation reduction equations can be balanced with the budget method, and they're very easy to balance. Sometimes they don't balance so easily because we've got electrons moving in the background. If we can account for those electrons and set the equation up so that we balance the electrons first, then the equations through half reactions, then the equations can be combined and you're done. Or sometimes you balance the electrons and then that's your new starting point for the budget method. Those are two possibilities. But for now, we're going to look at the half reaction method as a pure procedure. All right. The number one here actually skipped a step. Write the compounds and the polyatomic ions correctly for reactants and products. Then split them into oxidation steps and reduction steps. How do we do that? The way you do that is you assign oxidation states to each of the atoms and you see which ones change. And that tells you, right, if they become more negative, they're being reduced. If they become more positive, they're being oxidized. And you separate them out into two half reactions. Then you go through these following steps. Balance all the elements except hydrogen and oxygen. Balance the oxygens with water. Balance the hydrogens with H pluses, protons. Then balance the electrons. Now, as a practical matter, the only one that does need to come first is A. And sometimes we can balance the electrons first and then follow up with oxygen and hydrogen. With an example would be more instructive, I'm sure. Then, once you've balanced the half reactions, you've got to equalize the electrons. Multiply each half reaction by its independent number, whatever it takes, to give you the same number of electrons in the reduction and the oxidation reactions. Then you can add them back together. And after you add them back together, then you reconcile any excesses or any multiples that can be reduced to the simplest whole number ratios. All right, and there's your flow chart if you'd like flow charts. All right. So let's look at this equation and balance it. I think I've got it on slides, but it'll probably make more sense if I do it step by step on the board. So we got the dichromate ion, and there again, we left out the cation, right? It's probably potassium or sodium, dichromate. But sodium doesn't change throughout the reaction, so we just leave it out. It gets in the way. So here we have the overall unbalanced equation, dichromate, okay? And that's aqueous. And then we have the sulfite ion in aqueous solution. And then it produces chromium 3 plus ion plus SO4, the sulfate polyatomic ion. Okay? We know that these are the reactants and those are the products, but we didn't account for everything. not just the spectators, but you'll notice that we have 10 waters here. I mean, 10 oxygens here and only 4 there. And if we balance these oxygens with water, we're going to introduce hydrogen. So then we have to balance hydrogen too. Okay. This method, this first approach at half reaction balancing is what I call the acid half reaction method. And you'll see why in just a minute. Okay. Let's assign oxidation states so that we can determine which one is the reduction half reaction and which one is the oxidation half reaction. And so we have -2 for one oxygen, -14 for total. Then we have 2 negatives that must not be touched. So we only need to balance 12. That means +12 here or a +6 for each of the chromiums. All right. How about this one? -2 times 6 times 3 is -6. We have to hold out 2 minuses. So we only have to balance the -4 with a +4. Right? Chromium, it's already got its charge, right? That's a rule. It's a 3+ oxidation state. This one's a -2 times 4 is -8. We hold out 2 of them for that 2 minus. -6 is all we have to balance with a +6. Okay, now that we know what's happening, which one is oxidized and which one is reduced? Well, we see that chromium goes from +6 to +3. All right, how did it get there? We had to add 3 electrons, right? 3 negatives. So this is a reduction step. Reduction is gain. So the reduction step is this one. So 7, 2 minus. I'm going to put the oxidation states there so we can keep track of them. And I'm going to try to line up the arrows with this one. Okay. That means that the sulfur ions must be the oxidation step. Okay, we got this sulfite ion, the +4 here, and it goes to sulfate with a +6. And that figures. We go from a +4 to a +6. How did it get there? Remember, you can't touch the protons. So we had to remove, not reduce, oxidize. We had to remove 2 electrons. Okay? Now we've got our half reactions. Next step is to balance anything that's not oxygen or hydrogen. So chromiums. We have 2 chromiums here. We need 2 chromiums there. We got 1 sulfur here, 1 sulfur there. It's done. Now, we can either go to oxygens and hydrogens, or we can go to electrons. I'm going to take it in order that was given in the previous slide. So we'll do oxygens first. We have 7 oxygens here. We have no oxygens over there. So we need 7 oxygens. And we put those in as water. Okay. Now we've added 14 hydrogens on this side. We need 14 hydrogens on this side. So we put our hydrogens in as hydrogen ions, protons. Okay. Now this one has 1 oxygen extra over there. So we need to add 1 water here. That means 2 hydrogens here. Okay. Now we're going to balance electrons. So how many electrons moved? Well, if we have a +6 to a +3, that means we gained 3 electrons per chromium, but there are 2 chromiums. So instead of 3, we actually have 6 electrons. Okay? All right. So on this one, electrons on this side, we know electrons are going to have to be on that side, right, for an oxidation. So we went from +4 to +6. That means 2 electrons were lost from this one, and they show up here on the product side. Okay? Now we can balance the electrons. We have 6 electrons here, 2 there. How do we make them equal? They're both even numbers, so if we multiply this one times 3, all of it times 3, we get 6 electrons. So if we say 3 times, that makes a 3 here, a 6 there, a 6 there, a 3 here, and a 3 there. Okay? So now we have 6 electrons, and we can go ahead and cancel the electrons. That was the whole purpose. Then we can recombine the equation. All right. Now we bring them down. Dichromate. Right? Dichromate. Then let's put 3 sulfites plus 3 waters plus 14 hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. All right, let's put chromium first. 2 chromium 3 plus ions. I left out the aqueous solution. That's okay. It's all in aqueous solution. Then let's bring down the 3 sulfates. Okay. Then we can bring down 7 waters and hydrogens. We have 6 hydrogens. 6 hydrogens. Okay. Notice we've got water and hydrogen on both sides. So now we have to reconcile that. 14 hydrogens here, 6 on this side. No, 6 there. Remove 6 here means 8. Waters. We have 3 waters on this side. Subtracted from this one is 4 waters left over. Now we have a balanced equation. And subsequent slides should show you the steps that we took. There's the final balanced equation. Let's see if it's right. 4 waters, 3 sulfates, 2 chromium 3 plus, 8 hydrogens, and 3 sulfites, and 1 dichromate. Okay? That's the final balanced equation without the counter ions. We still don't have the cation that goes with this one, or the anion, the cation that goes with this one, or the cation that goes with that one, and so forth. The other point I want to make is this is all occurring in aqueous solution. So all of these species are in the same pot. All right. So we have these hydrogen ions and water. What does that mean? That means that this reaction takes place in acidic solution, right? Those hydrogen ions, just like Arrhenius would predict, or Bronsted and Lowry would predict. Those free hydrogen ions mean this is an acidic solution. Now I'm going to do something. We're going to talk about it in a minute with a separate slide, but since we have this on the board, suppose this is acidic conditions. Suppose you're told that this reaction takes place under basic conditions. Now what do? All you have to do is neutralize the acids, right? How do you do that? You add hydroxyls. So if we have 8 hydrogens, we need 8 hydroxyls on both sides. Okay? So what does 8 hydrogen, 8 hydroxyl give you? 8 waters. So this gives you 8 waters. Okay, now you have 8 waters here and 4 on that side. These waters disappear. And now you have 4, you have 4. So under basic conditions, I call this my fake acid method. You do the acid first, and then you convert it to base. Everything else is the same. We just have 4 waters on this side now and 8 hydroxyls on that side. And remember, they're all in the same pot. So these hydroxyls are available to everything. This environment is basic now. All right. So we'll come back to that method in a minute. I just wanted to show you, since we had it all here already, then it made sense to just show you how you convert to a basic environment. All right. So balance the following reaction in acidic solution. Right? So you just use the half reaction method for acid environment, and we should come up with the correct answer. Oh, okay. They just gave us the answer. Let's go through and, let's go through and do it. So here's our starting conditions. And this is all aqueous, so bromine's liquid, so I better put aqueous here. And manganate, right? Yield bromine liquid plus Mn2 plus aqueous. Okay. Now we have to do the oxidation states. That's a -1. That's a 0. That's a +2. This one, -2, -8. We hold 1 out for that one. So that means this is +7. You should be able to do it just that quick. All right. So bromine goes from minus to a 0. How did it get there? It had to lose a negative, right? Oxidation is loss. So we have bromine. Oops, that's 2. Right? Left out my subscript. Okay, that means reduction is what's left over. MnO4 minus. And this is a +7 oxidation state. And then we have manganese 2+ aqueous. Okay. We got 1 bromine here and 2 there. So we need a 2 here. 1 manganese, 1 manganese. We're good there. Now we do oxygens. No oxygens here, so we don't have to bother with this one. We got 4 oxygens here. That means we need 4 waters and 8 hydrogen ions. Now we can do the electrons. So if we go from a -1 to a 0, that means we lost 1 electron for each bromine, but there are 2 bromines. So we lost 2 electrons. If we go from a +7 to a +2, we had to gain 5 electrons. And there's only 1 manganese, so we gain 5 electrons. Okay? So now we have to reconcile the electrons, the number of electrons. What's the problem? Even, odd. In fact, prime. So remember back when we were setting up compounds and we were trying to balance charges with compounds, cross multiplication was a good technique. If we put the 2 over here and the 5 over here, that will give us 10 electrons and 10 electrons. And it will also change this one to 16, 2, 8, and 2. And change this one to 10. And change this one to 5. Like that. Okay. Now we can recombine. This is going to stay acidic. So I'm not going to mess with this one. I'm not going to bother showing you basic possibilities here. We just have, I'm going to put bromine first, minus aqueous solution. Then we have 2 manganate ions in aqueous solution. And we also have 16 hydrogens. Right? And the electrons cancel. Right? Now, what do we have on this side? Well, let's see. Let's do the bromine first. Br2 liquid. And then the 2 manganate, 2 Mn, 2 plus, and 8 water. Okay. So can we reduce this one any further? That's 10 to 5, 2 and 8. No, we have to leave it just like that. And it appears to agree with the answer on the slide. Okay. These are the steps for my fake acid method. You do the acid balance first, then you convert it to base. Now, theoretically, you should be able to do a half reaction method for base as well. The problem is when you're balancing oxygens and you add waters to balance the oxygens, now instead of hydrogens, you have to put hydroxyls. Well, hydroxyls have oxygen and hydrogen. So every time you balance the hydrogens, you add more oxygen, and it just goes back and forth, and it's an endless loop. So this is a more efficient way. Do the acid first, then convert to the base. And that's all these steps tell you to do. Go through the acid steps, and then this flow chart shows you the green at the bottom. The green is where you convert the acid balanced equation to the basic equation. All right. So let's clear the board. Okay, so this slide talks about what I just mentioned, the problems that arise with trying to balance directly to basic rather than going through the acid step first. Okay, what do we got here? Balance the following in basic solution. All right. Well, let me see which slide I'm on. I didn't pull my hard copies out. If we have time, then we'll do this one complete. I got to see what slide I'm on now. Okay, let's see. 18-1 cyanide manganate. Okay, so that's 19 out of 54. That only leaves me about an hour. Okay, we can probably do this one. I think we got enough time. So we're starting with cyanide. reacting it with manganate. And our products are CNO minus ion. It's obviously a polyatomic, and manganese dioxide equals. Okay. So we need oxidation states. Remember, if we're going to do carbon, we have to assume nitrogen is a -3. So we're holding one of the negatives out for that charge. Carbon only has to be a +2. -2, -8, hold one out, +7. Oxygen is -2. We have to assume, in this case, otherwise we're stuck, nitrogen is also a -3. So that together is a -5. We need one of those negatives here. So that means this oxygen is a +4. And -2, -4 total, this is a +4. All right. So now we can split our equations. If we go from +2 carbon to +4, that means it was oxidized. It lost 2 negatives. So the oxidation step is the cyanide ion at +2 and the CNO ion at +4. That leaves reduction step for the manganate at +7 being reduced to manganese dioxide +4. Okay? And I'll emphasize the fact, we're not saying that that manganese has a +4 charge. It has a +4 oxidation state. This is a bookkeeping scheme to track electron movement. This is actually, well, this is an ionic compound. This is not an ionic compound, all nonmetals. Right, so when we say +4 for carbon, we're not saying carbon has a +4 charge. We're saying that it has an oxidation state for our purposes of bookkeeping. All right, back to balancing. Carbon, carbon, nitrogen, nitrogen, we're good. Manganese, manganese, we're good. Oxygens now. One oxygen there, one oxygen here, and 2 hydrogens here. Right? 2 hydrogens, 2 hydrogens. 4 oxygens and 2 oxygens. That means we only need 2 more oxygens on this side. So we have 2 waters here. That means 4 hydrogen ions. Okay, now we can do electrons, right? What are the electrons' movements? Right, we did +2 to +4. That means we have carbon lost 2 electrons for each carbon. And on this side, manganese went from +7 to +4, means it gained 3 electrons for each manganese, right? A -3 and a +4 and a +7 is a +4. Now we balance the electrons. There we got an odd and even. So now we need 3 here and 2 there. Cross multiply. That means 3, 3, 3, 6, and 6. 6 and 8, 2, and 4, and 2. Okay? And the electrons cancel. Now we can bring everything down. In acid solution, this is before we convert. Cyanide first, we have 3 of them. 3 CN minus. And then we have manganate, 2 manganates. And we have how many waters? We have 3 here, none there, so this is 3 water. And hydrogens, we have 8 hydrogens. Yields 3 CNOs. Okay. And 2 MnO2. Waters, 4 waters. And hydrogens, 6 hydrogens. Okay. Now let's reconcile. 3 waters, 4 waters. Cancel those. Leaves us with 1. Okay. Hydrogens, 8 hydrogens, 6 hydrogens. Cancel those. Leaves us with 2. Now we convert the hydrogen ions to water by adding 2 hydroxyls on each side. Okay. That makes 2 waters on this side and 2 hydroxyls on that side, but we already got a water over there. So that one cancels, and now we only have 1 water. So balancing, we have 3 cyanides, 2 manganetes, 1 water. We have 3 CNO minus, 2 MnO2s, 2 hydroxyls. That equation is balanced. Now, we canceled the electrons, but the electrons are still there. They're just moving. It's important to keep track. Once you do this equation, if we're going to do anything with it quantitatively, like later we're going to say, all right, what's the voltage, right? What's the push? I have to define that for you. What's the push behind the electrons that are moving? We need to know the number of electrons that are moving. So keep track and don't actually throw them out of your brain. Just hang on to those 6 electrons for later. The galvanic cell is another way of saying a battery. A galvanic cell converts chemical energy into electrical energy. But how do we do it? Remember I said that all of these things are in the same pot. They're in the same solution. That means when those electrons move, that's where the energy is, movement of electrons. We don't have access to them because they're all in the same solution, right? We can't go in there and catch the electrons as they move and use them for energy. What we need is a method to move those electrons externally so that we can use them as they move to gain energy. And that's what the galvanic cell does. It separates the half reactions into separate physical compartments, and the external connection delivers the electrons from one half reaction to the other. Now, in order to do this, the reaction has to be spontaneous. In other words, it has to be that way. Recognizing that it is reversible, but if we let it go on its own, spontaneous is what we're looking for a galvanic cell. Spontaneous is the only way we can catch that Gibbs free energy. All right. Recognizing also that when we separate these into 2, we're not going to use this equation, so let me erase this. When we separate the 2 half reactions into physical locations, that the oxidation and reduction reactions still take place, but they take place at the electrodes. Right? That's the point at which electrons are either moving out or adding to the solution. So if electrons are moving from this direction and that direction, right, and we have a meter here that tells us that they're moving, and these electrons are moving that direction. That means when they arrive here, they're going to reduce something. So this is where reduction takes place. This is where oxidation takes place. Because electrons here are moving into that electrode, and here they're coming out of the electrode. Okay? There's another detail I have to give you in just a second. And that is, anybody who's studied electricity knows that you cannot get electrons to move unless you have a completed circuit. They have to have a pathway all the way around back to where they started. That means we need some type of bridge between the two solutions to allow the circuit to be completed. Right? If we break that, if we remove that, then no reactions take place because we broke the circuit. Now, what I showed you here is a salt bridge. We put something into this thing and we plug the ends of it, or we mix it into agar and fill it up with agar just to keep it from exchanging en masse anything from this side and that side. All we want to move is ions. The other way you can do it is put a porous disc between the two. Then you can connect with you through the ions without wholesale exchange of fluids. Now, as a practical matter, the porous disc is a less resistance to movement of ions, whereas the salt bridge is a greater resistance. So what that does is it reduces the efficiency of the cell. The porous disc is much more efficient. That's a galvanic cell. These are half cells. The whole thing together is the galvanic cell. Usually the salt bridge, if we have using a salt bridge, it's composed of a strong electrolyte. We need a strong electrolyte. That is something that decomposes, that separates into cations and anions completely, like sodium chloride, potassium nitrate, things like that. And you have to choose that electrolyte wisely, because if you choose chloride ions in here and you have silver on either side, that reaction is going to take precedence. Remember, the solubility product of silver is very low. So if you put chloride in here and you have silver on one of these sides or the other in solution, then it's going to react and precipitate out, and you get no reaction. Right? So we would use nitrate in that case rather than chloride. All right. So typically, the way we set up the cell diagrammatically is to put the, wait a minute, I did the wrong, I got them backwards, I think I got them backwards. No, reduction takes place on this side. So this is the oxidizing agent side. I did put them in the right order. Our oxidizing agent is on this side, and the reducing agent is on this side. Because it undergoes oxidation, this oxidizing agent undergoes reduction. And the electrons move clockwise. Okay, so we've got another name here. This cell over here is called the cathode. It's always, the cathode is always the site of reduction. The site of oxidation is always the anode. regardless of what you're doing. If we force the electrons back this way, now this side becomes the cathode and that side becomes the anode. It's always based upon what's happening. Reduction, cathode. Oxidation, anode. All right. Now let's talk about cell potential. Sometimes we write it, if we have access to script font, then we can use that fancy curly E. Otherwise, we just write a big E, which means electrical potential, cell potential. And the unit of measure for cell potential is the volt. Think of it as a push. How strong is the push behind those electrons to move from the anode to the cathode? The stronger the push, the higher the voltage. Or you can think of it as a pull. Either way. I like to think of it as a push. Sometimes they refer to it as the electromotive force. And the unit of measure is the volt. Now, what the volt actually means in terms of its value and interchangeability with other SI units is the volt. 1 volt is equal to the amount of work, 1 joule of work, 1 joule of work, 1 volt, 1 joule of work for every coulomb of charge. Right? Abbreviated C. So 1 volt will produce 1 joule of work for each coulomb of charge that moves. And this can either be a movement of electrons in our case, or it can be a movement of any ion. So it's more generalized, actually. Now, what you'll see in textbooks is this is the unit of measure. If we put it in an equation, then we don't use that V. It's given a U. U is the value of is the symbol for electromotive force. And that's equal to a joule per coulomb. And then the unit of measure is the volt. But sometimes you'll see the V substituted for that also. You can see it both ways. I just wanted you to recognize that fact. Oh, I got a video. The sound may not be too good, so the recording, I'll substitute the original video in the processed recording.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The 2 solutions are connected by a porous sodium chloride salt bridge that prevents the 2 solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
All right. So, in that arrangement, the cathode was the half cell with copper in it. The anode was the half cell with zinc in it. And the electrodes, zinc and copper, are participating in the reaction. That doesn't always have to be. Remember, we showed you half reactions where there were no solids at all. Everything was in aqueous solution. So in those cases, you need something here to conduct the charge. An electrode, it doesn't participate in the reaction, but it does allow for movement of electrons. So we would substitute something like platinum, right, which is inert. Platinum on either side of for the half reactions that we studied earlier. And notice that as zinc ions are being produced from this zinc electrode, the mass of the zinc electrode is decreasing. We're putting zinc into solution. Whereas here, we're reducing copper 2+ ions to copper metal, and the copper electrode is increasing in mass. All right. Let's see. How do we measure cell potential? Well, there are a couple of different ways. Actually, there's more than two. But measuring the cell potential can be done with, for our discussion purposes, the use of a voltmeter. Voltmeter is the cheap way. Actually, we rarely ever see voltmeters anymore, standalone voltmeters. They're usually multimeters now. They'll determine voltage, they'll determine resistance, they'll determine amperage, and they usually have a circuit tester involved. If you set it on circuit test, then you put the two electrodes on either side of your say light bulb, and if it buzzes, then the filament is still good. If it doesn't buzz, that means the light bulb has a broken filament, for example. Voltmeter produces a value of electromotive force. Resistance is what's the resistance to movement of electrons in the circuit. And amperage is given the symbol of I, which means amps or flow of electrons. How many electrons are moving past this point in 1 second? And grandfathered in is this unit of measure, the coulomb. The coulomb is a certain value of charges. It could be negative charges, it could be positive charges. A coulomb is just a number of charges. It's a very large number. And we have a conversion factor that I'll show you in a minute between coulombs and moles of electrons. But the voltmeter, how does the voltmeter work? Well, you attach the leads of the voltmeter to one side or other, actually both sides of your circuit, and it measures the force pushing electrons. The way it does that is it has a calibrated resistor in the circuit. Right? So if you have a source here, we identify that like this. like a battery, and you have your voltmeter here. This could be a galvanic cell, for instance. Then it's gonna have a resistance here. And let's see, I painted myself into a corner. I'm trying to remember Ohm's law. V equals I R. Or if we rearrange that, let's see, R, if we make R constant, R would be constant here. And then we have volts over amperage. Okay? So we have this standard resistance. The circuit is designed to measure the movement of electrons. So if it gives us a certain amperage, then that is calibrated to read out as voltage. This is the least expensive way to determine voltage in a circuit. The problem is all this circuitry has what's called internal resistance. And as long as electrons are moving, that resistance is fighting their movement, and we're not measuring that at all. So the value that you get by measuring this way is less than the true voltage. The true voltage is a little bit higher. The only way that you can get true voltage is to reduce the movement, the flow of electrons down to infinitesimally small value, down to zero. We can't do that with this circuit because if electrons aren't moving, we can't measure anything, right? So that's the problem with this one. It's cheap, but it's less accurate. So if you need accuracy, oh, that's called current. Let's see, amperage current. If you need accuracy, then you need to shell out some more money. And that's where the potentiometer comes in. The potentiometer has an adjustable dial, and it applies a reverse voltage. It has a calibrated system in it so that you can modify the voltage in the reverse direction. And you have a needle here. On the older models, you have a needle here. This is the 0 point, right? If you've got too much voltage coming through as opposed to the reverse voltage, right? You've got the measured voltage here, and you got the opposing voltage here. Then if this is not big enough, then this is going to show you a value over here. So you gradually increase the reverse voltage until you get 0. And your dial is calibrated so that it will measure the required voltage to stop current. So now we're at 0 current, and this is the true voltage. Because once you stop movement of electrons, you no longer have the problem of internal resistance. Okay? And this circuitry is much more expensive to produce and calibrate. In fact, you have to have it periodically serviced to maintain its calibration. That's why you don't find potentiometers except maybe in research labs. Right? The electrician that comes to your house is going to be using a voltmeter because that's good enough. All right. This is what a digital voltmeter looks like. And most digital voltmeters nowadays will measure in plus voltage and minus voltage. So if you get the leads swapped on the wrong electrodes, you may end up with a negative voltage. And that just tells you you just need to reverse the voltage to tell you which one is the anode and which one's the cathode. But it'll still give you a value. All right, what are standard reduction potentials? And why do we need them? Since all half reactions can either be oxidation or reduction, and you can only measure a voltage if you have both of them, you have two choices. You can set up a galvanic cell with every possible combination of half cells and just measure the voltage. Under standard conditions, that would be concentration of 1 molar. And if there are any gases involved, they're delivered at 1 atmosphere pressure. Excuse me. And at the standard temperature, 25 degrees Celsius. Those are standard conditions. And we could do that, if we had a large enough workforce, we could, every possible combination. But if you come up with a new combination, a new half reaction, what do? Well, you got to go through the whole thing again. So to simplify things, we measure the voltage for reduction against a standard cell. And the standard cell compared to what? Is the hydrogen electrode, the standard hydrogen electrode. So we would say like this, like that, and we have our bridge, our solutions, right? So we have, say we put something on this side, because this is where reduction takes place. This is the cathode, right? And this is a hollow tube with an electrode in it that connects with this one, right? And we have our voltmeter. And what we're delivering here is hydrogen gas at 1 atmosphere pressure and 25 degrees C. And on this side, we have a 1 molar concentration of whatever solution is appropriate for that electrode. Okay, and then we measure the voltage. The arbitrarily set voltage for the hydrogen electrode is 0 volts. So that means the half cell here is 0. So whatever we get here is the voltage for that half cell. That's known as the standard reduction potential. It can either be positive or negative. And we write the equation, the half reaction, as a reduction, always. So if this were copper, then we would write copper 2 plus 2 electrons yields copper metal. That would be the half cell expression for this, and it would have a voltage, some voltage assigned to it, based upon its comparison with the standard hydrogen electrode. Okay? And we've got tables filled with these numbers. So that standardizes the situation. If you come up with a new reaction, all you have to do is compare it with hydrogen. Now, if we want to compare two different ones, I'll show you how to do that in a minute. Then we say, all right, we're going to put something else in here. Say we put zinc in there now. It has a half reaction voltage. This one has a half reaction voltage. We just have to decide which one needs to be written with the electrons on this side and which one needs to be written with the electrons on that side. Then we can combine them. And the rules that tell us what to do with the voltage when we flip the equation. All right. All these half reactions are under standard conditions written as reductions. Right. I think, I'm not sure, this slide is kind of old. It was table 18.1 had those standard reduction potentials for a large number of half reactions. If we have to reverse, say we have to flip this equation, put copper on this side, copper 2 plus on that side, we just change the sign of the voltage. And we write, this is standard, where we have that little zero up there. That means standard conditions. However, this is an intensive property. So no matter what we say about, say we have to multiply the equation by a factor, say 2, 3, or we have to cut it in half, divide by 2. Whatever we do to the equation does not change E0 because it is an intensive property. It's not affected by the amount. So the E0 doesn't change. Now, if we need to know the exact value for other conditions, then it will change. But for standard conditions, no matter what you do to the equations, the standard reduction potential does not change, except in sign if you flip the equation. Okay. Now, the way I look at it is, if we want to compare this reduction potential to this one, and it has its voltage, what do? Well, the value that you get, a spontaneous reaction in a galvanic cell, requires that the voltage is always positive. So if you add these two together, if you say flip this one and change the sign and add them together, you get a negative number, you flip the wrong one. So you go back, put it back the way it was, flip this one to give you a positive value. That's how I look at it. Now, your book has an equation, which is fine if you want to memorize that equation. But here are the standard reduction potentials from the most positive to the most negative. So fluorine reduced with 2 electrons is the highest one in this chart at 2.87 volts. Against what? Against the hydrogen electrode, 0 volts. So this would be reduction. The hydrogen would be oxidation, the anode. And put them together, add them together, you get plus 2.87. If that were the case, fluorine being reduced to fluoride, then you would get a cell potential under standard conditions of 2.87 volts. And then we have a whole bunch of others. And I split them up into separate tables. There's our 0, right? Hydrogen plus 2 electrons yields H2. That's the standard reduction potential for hydrogen is 0. So the nice thing about that is, if you have to flip the equation on hydrogen to make it an oxidation, then it doesn't change because it's 0 to start with. The greatest one is lithium. Now, in four-year colleges and universities where they're training chemists, you would have to memorize what's called an activity table with the various metals. And one metal would be more active than another. The more active metal is the one that loses its electrons more readily. So in that case, lithium would be the most active metal in this list. Potassium would be a little less active. Sodium would be less than that, aluminum less than that, zinc less than that. And notice zinc is here, right here. We combine zinc with, say, let's see, where's copper? Copper here. Notice that it's a more positive voltage. It's lower on the table. so to speak, lower activity. So that means that zinc is the one that would lose electrons, and copper is the one that would gain the electrons. But I'm not going to have you do that. I'm just explaining that to you so that if you ever encounter activity, metal activities, conversation, you'll know what they're talking about. All right, this is the equation that comes from your textbook. If you want to know the voltage of this cell under standard conditions, you take the voltage of the cathode and subtract the voltage of the anode. So if the anode happens to be negative, it becomes a positive. And the cathode might be a negative, but if it's the cathode, then the anode is subtracted from the cathode value. And the way you decide which one is which is, that's why I say it's easier for me. If it's written correctly, then you just look at the cathode side and the anode side. But it makes more sense to me if you have both of these reduction reactions and you flip one and you get a negative value for the sum, that you flip the wrong one. So go back and flip the other one. And then that becomes the cathode. Excuse me. No, the cathode is the one you didn't flip because it's the reduction. All right. And these are just standard reduction potentials. Right. So what would it be for this example? Well, what are the half reactions? We have iron 3 plus going to iron 2 plus. As a reduction potential, we have 0.77 volts under standard conditions, whereas copper solid would be on the product side. In the equation, it's on the reactant side. All right, so we can probably assume that that is going to be the oxidized. Copper is going to be oxidized. But if we write them both as reductions, we get 0.77 and 0.34 for each one. Now, which one do we have to flip? Which one do we make negative so that we get an overall positive? We flip the second one. So now it's copper yields copper 2 plus 2 electrons. And then that flips the sign. We add them together. Right? And we get, excuse me, it's not finished yet. There we go. That's the balanced equation, right? And that can be useful. It also tells us how many electrons moved. Once you get the equation balanced, then you can assess, in the process, you assess the number of electrons that move. In this case, 2 moles of electrons move in this case. But the overall voltage, the cell potential, under standard conditions is still 0.43 volts, right? A little less than half a volt. Okay. Well, yeah, why should we care? Well, later we're going to see how a quantitative transfer of electrons have to be considered to assess the actual cell voltage, right? Every cell is not going to be 1 molar concentration, 25 degrees, and 1 atmosphere pressure for gases. So we want to be able to calculate the actual cell voltage. That's where the Nernst equation comes in. The Nernst equation allows us to calculate the actual voltage under any conditions that you decide. And it also allows us to assess the stoichiometry of electrolysis reactions. That is, those that are galvanic in one direction, we force them back the other direction simply by reversing the voltage. We add an external voltage that exceeds the voltage of the spontaneous cell. All right. This is going to be, I've questioned myself about this slide and subsequent slides about which one is the strongest or weakest oxidizer. It's a valid exercise for gaining insight into the standard reduction potentials. But as a practical matter, it's not as useful as I'd like it to be. Let's see. Well, where are they? Here we go. 2, 4. Let's try this one and see if we can make sense of it. So we want to order these from the strongest to weakest oxidizing agent. We're going to hold the Nernst equation until later. We're going to get there in just a minute. So we want strongest to weakest oxidizing agent. So this is strongest to weakest oxidizing agent. What does that mean? The strongest oxidizing agent is the species that's most readily reduced. If it oxidizes, it is the most readily reduced. And that would be the least readily reduced. So what does that mean? Well, if we know the standard reduction potentials, then we can make a comparison. So we order from the largest positive standard reduction potential. The largest standard reduction potential will give us the most readily reduced. All right. So notice that if we reduce something, it has to gain electrons. So which one of these would actually accept electrons being gained? Well, sodium, yeah, it's a positive ion. Chloride is a halogen. They like electrons. Oh, yeah. Sodium metal doesn't like to gain electrons. And iron doesn't like to gain electrons. So they'll be the least readily reduced. Iron and sodium metal should be on this side. Fluoride should be even further to the right because it's already got all the electrons it wants. So we should have iron down here, sodium down here, and fluoride down there. Right? We should have sodium and chloride and chlorine up here. Sodium ion and chlorine up here. That's just a general division, right? Okay, so now let's see if we can quantify it. We don't know values for this one. Let's see. We don't have values for sodium, fluoride, fluorine, or let's see. We don't know values for. Here's what we do know. For reductions, right? We're comparing reductions. Which has the most positive value for reduction? Well, F2 is not in there. F minus is. So we would have to flip that one, and that'd be a minus 2.87. All right. I wonder why we left that one out. The value for Oh, okay. So we're not there yet. We're still saying fluoride ion would be reduced. We don't know what that is. So I'm saying it's going to be the farthest to the left, simply because it's a negative ion. And it's going to be difficult to reduce it because with one electron added to fluorine, what do you have? You have an octet, right? It doesn't want any more electrons. So it doesn't matter if we have a value for that one or not. It's going to be on the far right anyway. Sodium, on the other hand, we should know what sodium will do to make an ion. Well, sodium ions, sodium plus electrons, that's not going to happen either. But I think it would probably be a little less likely than fluorine. I mean, a little more likely than fluorine. Chlorine, on the other hand, does have a value, right? So this one is 1.36. It's positive, very positive. And sodium ion is minus 2.71. So it doesn't want that electron. That's my mistake. This one, since it's a very large negative number, should be down here. Right? Sodium ion. That's probably not going to be the right order. I think maybe sodium ion should be here. All right. See what I mean about this not being very useful? Excuse me. Chlorine is going to be the greatest. We know that. It has the most positive value. Iron is going to be a little less. It's going to be in here somewhere. Right. Sodium ion, we're going to put on this side. Let's put iron here, sodium ion here, right? Chlorine there. And who's left? Fluoride ion. Fluoride ion goes on the far right. So the only question I have is maybe these two right here. Since we don't have a value for them, we have to sort of rationalize it. Right? See what I mean? Okay, chloride is a strong oxidizing agent. Yes. Stronger than sodium. Other species don't have standard reduction potentials to compare. The remaining fluoride, sodium metal, iron metal should be easily reduced. So this one is the strongest. And we had four, 1, 2, 3, 4, I had 5. I left out, left out sodium here. Metals typically don't want electrons. And so there it is. Now there's a standard way. Remember, we wrote, or we put together a galvanic cell with a reaction on this side, a reaction on that side, and a salt bridge between them. There's a standard way to write these in shorthand notation. That's called line notation. And line notation is standardized for the cathode on the right-hand side, anode on the left-hand side. And we separate them by a double vertical line. The double vertical line is either a salt bridge or a porous disk. Okay. Yeah, I spell it with a C, they spell it with a K. That's fine. We'll make it a K. A single vertical line on either side here is a phase difference. This is a phase change. That vertical line. So on this side is cathode. And this side is the anode. Okay, so which way are the electrons going to flow? Electrons are going to flow from whatever's out here, around here, to this side. Like that. And if you know what the concentration is, you should specify it in the notation. And we'll give you examples in a second. So here's a generalized one where we're showing the phases of each of the things. So in this one, we have magnesium here. We have the magnesium 2+ ion here in aqueous solution. And then just across that salt bridge is the other ion, aluminum. And the electrode on this side is aluminum. So electrodes are flowing here through this electrode, external circuit into that electrode, and that's where the reaction occurs. We don't know the concentration, so that's as far as we go with it. That's the anode, that's the cathode. Now, the number of electrons we can deduce from their oxidation states. Right? This one had to gain 3 electrons. This one had to lose 2 electrons. So we can write the half reactions. I mentioned earlier, if the electrode does not participate in the reaction, then we put it into the expression here. Say we have, well, that's not a good example. We might use a graphite rod or platinum. Dry cell batteries, they have a graphite rod in them because the reactions are all occur in solution. But we can use a platinum rod sometimes if we can afford it. Let's see. Here's a case where we have silver as the possible electrode, and we have the standard potentials for these 2 reductions. Which one do we flip? We flip the iron because making it negative gives us an overall voltage for this galvanic cell of 0.03 volts. Okay, so once we know that, we know that the anode is going to have iron 2+ going to 3+. So it's going to be, let's see, let's put it like this. Iron 2+ going to iron 3+. Notice there's no phase change between the two. But we do have a platinum electrode change in phase there. And on the other side, we would have silver. So we would have silver 1+ and silver solid. There. So that's how you would write the line notation for a reaction in which one of the half cells doesn't have a participating electrode. Okay, let's see. I've already talked about that. All right, so here we go. This is what it would look like in a picture form. And what it should look like, let's see. Line notation. Here we go. Yeah. All right, they put 2+ and 3+. I think it should be this way, 3+ and 2+, because we're saying electrons are going this way. So they're moving from this one and leaving behind this one. Or maybe they just arbitrarily pick 2+ and 3+ the way it is. But you separate them with a comma. because there's no difference in the phase. Actually, we know this is the anode, right? So we know we're going from a 2+ iron to a 3+ iron. That's given anyway. All right, plus the phase separator. Let's see. Right, cell potential is always positive for a galvanic cell. The balanced cell reaction is always composed of the half cell reactions with electrons balanced. And then we introduce, in our line notation, we introduce the non-participating electrodes if necessary. All right. So if we sketch a cell, in this case, I used a program, I forget the name of it, but it allowed me to produce this cathode on the right, anode on the left, and the overall voltage has to be positive in order for this to be spontaneous. All right, now using this as an example, and we're eventually going to get to the Nernst equation. I've only got 20 minutes left, and we're on which slide? At 6. Okay, I've got quite a few slides left, so I'm probably going to run out of time. Let's see, did anybody else show up that I haven't counted for? No. And didn't show up, and Madison didn't show up. Okay. What would happen in this case where we have copper, you have silver in the cathode and copper in the anode, and we know that it's spontaneous in that direction under standard conditions. But what would happen to the cell potential if we increase the copper concentration? Right? If we increase the copper 2+ concentration, Le Chatelier says we're going to drive the reaction backwards toward making copper metal. Now, what will that do to the availability of electrons, the movement of electrons? Well, if we move it back toward the copper, it's going to consume electrons, right? So if we do that in the anode, we increase the solution concentration of copper 2+, the overall cell potential should go down. It should decrease because we're starving the circuit of electrons. Right? So that's what's going to happen if we happen to set up our galvanic cell with a concentration greater than 1 molar. It will actually decrease the value of the cell potential. Now, we're still on our way to the Nernst equation. We just need to detour for a moment. What's the relationship between work and cell potential? Because we need to know how much work can we get out of this galvanic cell. If it's a very low voltage, I suspect that we're not going to get a whole lot of work out of it. And here's the relationship, right? Well, the cell potential is work per unit charge, right? Joules per coulomb. Remember this expression, right? Voltage of the cell is work per unit charge. This is work, energy, and this is charge, Q. Now, when we were studying thermochemistry, we used Q as heat, right? When we were studying thermodynamics, Q was heat. But in this case, Q means charge in coulombs. So since E, in order to be spontaneous, E must be positive. Remember, if we're getting work out of this system, right, that means W is going to be negative because it's leaving the system. But E has to be positive, and the charge is always positive anyway. So we have to say, all right, if we're going to use this expression, this equivalence, then we have to say negative. We actually have to put a negative here. Right? Work, the voltage is the amount of work per unit charge. So in order to keep the sign convention stable, we have to introduce a negative value. And Q times E equals negative W. So if we know the charge that's moving, the amount of coulombs, and the voltage, we can calculate the work. And the maximum amount of work we can get out of this thing is equal to negative Q times voltage. Okay, and Q has to be in coulombs. Okay. All right. The work performed per unit charge is equal to the voltage. Let's see. Okay, this is the maximum amount of work, right? And we know, we've learned from the last chapter that you'll never get maximum. There's always some waste of energy in a spontaneous process. All right. So here's the relationship. It's called the Faraday. 1 Faraday, and this is named after Michael Faraday, who did a massive amount of work on electricity in his day, is equal to 1 mole of electrons is equal to 96,485 coulombs per 1 mole of electrons. That's the conversion factor, 96,485. And it's in useful information, so you don't have to memorize it. Okay. Now, if we look at free energy, the change in the maximum amount of work is equal to delta G. So we can say this is also delta G, change in free energy. So for a galvanic cell, there's your equation. And since Q equals the number of moles times Faraday, so if this is charge, this is Q, this is the number of moles, and that's a Faraday, then we can say that Q here equals the number of Faradays times the number of moles of electrons, NF or FN. Then we can substitute in this equation for Q, NF for Q. Yeah, then that means delta G is equal to negative N Faraday times maximum voltage. So this is a good equation to remember, and this is a good equation to remember, or know what it means so you can look it up. There's Michael Faraday. He was a young fella. He was self-educated too. He didn't have a college degree, but he eventually became a member of the Royal Society of England. And that's a very prestigious position to work your way up, being self-taught. In other words, he was a genius. All right. So we're saying that the maximum cell potential is related to the free energy difference between the reactants and the products in a cell. So and this is positive, that's positive, that's positive. So we still have to have the negative. And the delta G under standard conditions is equal to the E under standard conditions times the Faraday constant and the number of moles of electrons that move in the reaction. So here we are. When we calculated the number of moles of electrons before we recombined the half reactions, that's the value that goes here. All right. So what we're saying is, if this is positive, then that makes delta G negative, and that means we have a spontaneous reaction. The cell will deliver electrons from left to right as written. Now, before we get to using the Faraday equation, we need one other concept. It's called the concentration cell. The concentration cell has the same chemistry in both half cells. Now you might think, well, how's that going to work? Right? It works because the concentrations are different. If the anode has a much lower concentration of ions in the cell than the cathode, then you're going to get a positive voltage. All right. Le Chatelier says that the lower concentration will increase and the higher concentration will decrease. So you start to get more silver, in this case, more silver ions in solution from the anode and more silver being deposited on the electrode in the cathode. Because the cathode has a higher concentration of silver and the anode has a lower concentration, the reaction will proceed from lower to higher. Okay, here's Walter Hermann Nernst, obviously German. He worked in he had his fingers in lots of different pies. Thermodynamics, physical chemistry, electrochemistry, solid state physics. So he developed other theories that were just as useful. And in fact, they won him the Nobel Prize for his work on the third law of thermodynamics. And his Nernst equation came before that, 1887. What is the Nernst equation? Well, here's the third law of thermodynamics. We got that one in last chapter. If you have a perfect crystal at 0 K, right, absolute zero, then its entropy value is 0. That's your reference point. So the Nernst equation allows us to calculate the actual voltage, not the standard voltage, but the actual voltage of a cell based upon concentrations. So let me put this over here. The Faraday is 96,485. That's the Q value. This is coulombs per 1 mole of electrons, which would be N. See, this is Q. There we go. Okay, now we can erase this. Okay, here's the Nernst equation in all its glory. If we know the standard potential, and we know other factors, we know the R value, the gas constant, and this is the one with joules in it, 8.3145. Temperature in Kelvin. We know the number of moles of electrons that are transferred in the reaction, and we know the Faraday constant. And we also know Q for the reaction. So we need to know the balanced equation. We need to know the concentrations of reactants and products at the start, not at equilibrium, but at the start. Calculate Q. Then we can introduce those factors in here and find out what the true voltage is. Now, as a practical matter, right, if the temperature stays at 25 degrees, this is not going to change, right, from this situation. So we can say that's a constant, this is a constant, and we can combine R, T, and F together. And if we do that, we get 0.0591. Divided by N, and then the natural log. Actually, we also want to convert the natural log to common log. That's easier to work with. So now we have common log Q. And we still need the standard, and this will tell us, and this is the equation that we're going to use right here. Right? If we were going to be chemical engineers, right, we'd keep this one right here because these values change. Temperature changes a lot. Okay. And that little blue box on the right is just a proof. Right? You don't have to memorize that. It just proves to you that this factor that I incorporated, 2.3026, times the common log equals the natural log. And I've just drawn that, proved that in this thing right here. So take it or leave it. All right. So at 25 degrees, an equilibrium, Q equals K, correct? And at equilibrium, the reaction is no longer proceeding. That is, no voltage. Right? You only get a voltage if you have a Q that's not equal to K. So now we can substitute. The actual voltage is 0, but the standard voltage is still what it is. And we substitute K. So now, if we know the number of moles of electrons moving and we measure a standard potential, we can calculate K. Or if we know K and the number of moles of electrons that are moving, we can calculate the standard potential. Right? It's like any formula. Right? Any equation, if you know all the variables except for one, you can solve for it. All right. So I got 5 minutes officially. I know I'm going to run over, so if you have to go, that's fine. For this oxidation reduction reaction, the appropriate half reactions are given, and the standard cell potentials are given. So which way do we flip? Right? We flip the chromium so that we get a positive value. Then balance the redox reaction and calculate the E and K. All right. So E is easy, right? We just flip the bottom, the chromium equation to make it the anode. That changes the sign, and then we get a value of 0.67 standard potential. That would go right here, 0.67 volts. Okay. Now, how many electrons moved? Right? 2 moles of electrons. So this is going to be 2 moles. Right? If we let it go to equilibrium, okay, here we go, 2 moles, N equals 2. If we let it go to equilibrium and change this to K, And log K. Standard potential. Got this one. What's the actual voltage? Oh, the actual voltage is 0. Yeah, this is at equilibrium. So now we can solve for this unknown, K. And it turns out that for this reaction, the K is 22.6. 22.6 is a huge value for K, which means the reaction is going essentially to completion, all the way to the right. All right. Oh, excuse me, the log K. Yeah, the log K is 22.6, excuse me. And when we solve for K, we get 4 times 10 to the 22nd, which again means all the way to the right. This is a spontaneous reaction that goes to completion. The only thing we have to worry about is running out of resources. And this is not unusual. Very large K values are typical for redox reactions in the spontaneous direction. Okay. What's the difference between E and E0? When is E equal to 0? During equilibrium, right? Dead battery, so to speak. When is E0 equal to 0? Concentration cell, right? E0 is always cathode minus anode, right? And if the cells are exactly alike, then E0 is the same for both of them, and the value is 0. All right. So here we have an example of a concentration cell, and the concentration in the cathode side is 1 molar, and the concentration in the anode side is 10 to the minus 4th molar, right? So in order to set up this reaction combination, this redox reaction, so that we can tell them apart, we use a subscript of C for the cathode side and a subscript of A for the anode side. Then we can determine anode over cathode is the Q. For the nickel, right, the solid doesn't count, right? It's the same as any other equilibrium expression, the mass action equation, right? The solids don't count, pure liquids don't count. So we only have to ratio the concentrations of the nickel 2+ ions. And if we do that, then we get this expression where we can calculate the actual voltage for this cell. Under these conditions, this concentration cell produces 0.118 volts. Now, most multimeters have a scale set. You can change the scale. If we change the scale to millivolts, what would that be? 1, 2, 3. 118 millivolts. Okay. Remember, the unit gets smaller, the number gets bigger. That tells you which way to move the decimal. Okay. Let's see. You make a galvanic cell, a nickel electrode of 1 molar nickel, and silver electrode at 1 molar with a potential of 0.8, positive 0.8. These are reduction potentials. So we flip the nickel. The nickel becomes the anode. Well, it tells us to do the line drawing. So the anode is going to be the side where the solid is converted to the nickel 2+ ion. And the right-hand side is going to be where the silver ions are deposited on the silver electrode. That's the cathode side. And this is what it would look like if you actually drew it out. Did it ask us the overall voltage? Should have. Yeah, there it is. 1.03 volts is the standard potential for that cell. All right, then we're going to say a little bit about batteries and then a little bit about, and I'm past time, so a little bit about practical galvanic cells that we use every day, and then a little bit about electrolysis, where we drive the reaction in reverse. So this is a lead acid battery. And all cars, except electrical vehicles, have this battery in them. This is simply to drive the accessories in the car and start the motor. And we have two plates in there. One is lead, and the lead is the anode. And lead oxide is the cathode, right? So, and common between them is sulfuric acid. Now, the fact that sulfuric acid is the electrolyte for both half cells means that we don't need anything to separate them. That's the great thing about the lead acid battery. We don't have to have a porous disc or a salt bridge of any kind, because they both share, the half reactions share sulfate, sulfuric acid in their reaction, half reactions. So this is the overall reaction. We have lead, lead oxide, and sulfuric acid makes lead sulfate and two waters. So let's see. No need for a salt bridge of any kind, right? When the battery is fully discharged, both the anode and the cathode are converted to lead sulfate. Now, as a practical matter, they don't have to be completely converted to lead sulfate. That's the ideal situation. The problem is that your electrode here and here, right, will deposit lead sulfate. Let's see, is that right? Yeah, will deposit lead sulfate on both electrodes, right? It's a solid. It's deposited on, and as long as it's touching the electrode, then we can run the reaction in reverse and convert it back into lead oxide here and lead here. The problem is the solution has to get to the electrode in order for this reaction to proceed. If it can't get to the electrode, if it's coated with lead sulfate, both electrodes, then the battery is said to be sulfated out. That is, the solution can't get to the electrode, so the reverse reaction will not proceed, and you cannot recharge it. It has to be recycled. Now, battery designs have improved over the years, so that we've usually by the composition of the plates, the lead and the lead oxide plates, and their geometries, their physical dimensions have been modified so that this is less a problem now than it has been in the past. But it can still happen. Okay. This is your dry cell, right? So there's your cathode is a carbon rod. That rod does not participate in the reaction. And the casing is made out of zinc. The zinc does participate. The zinc casing is the anode, which means what? As the reaction proceeds, the casing is being eroded. Right? That zinc is being converted into zinc ions. So theoretically, you could reach a point where you use up all the casing and you develop perforations in it. Maybe that's why they put a plastic coating on the outside. But the reaction itself occurs at the cathode carbon rod and at the zinc surface. And all that's holding, we call them dry cells because if you punch a hole in it, it doesn't leak. But it still has to be in aqueous solution in order for the reactions to proceed. So it's not really a dry cell, dry in quotes. All right, here's another possibility for a battery that we don't use anymore. The reason is because it has lead. It has mercury in it, excuse me, mercury. But there are other substitutes. You'll find these in calculators, in watches, in hearing aids. Not the lead, not the mercury battery, but a substitute for that. I think they use silver now. This is another possibility. It's called a fuel cell, but it's still a galvanic cell. We've got oxygen coming in on the one side, hydrogen coming in on the other. So what's happening to hydrogen? In this cell, hydrogen is being oxidized. I think. Yeah. Let's see. Yeah. And oxygen is being reduced. So oxygen is being reduced to 2O2 minus. All right. Now that's not the true half reaction, simply because what we've got going on here is the hydrogen and the oxygens combined to make water. So the product is water or steam because it's really hot. But the oxygen is being reduced, it's the cathode, and the hydrogen is being oxidized. And you get an electrical current. Now, the nice thing about this fuel cell is that it's going to be producing voltage as long as you supply it with hydrogen and oxygen. It can never run out unless you shut the valves, right? Or like Apollo 13, right? Unless you stir the tanks and one of them blows up on you. Corrosion is a spontaneous process, and corrosion is a special type of redox reaction in which a metal is converted to its ion. It's oxidized. The metal is oxidized to produce corrosion. Here's what it looks like on the surface of iron or steel, right? You set up a galvanic cell on the surface with a water droplet, and the anodic surface erodes the metal, just like any anode, and the cathode produces rust. Right? So the mass increases on the cathode side. The real problem with iron and steel in the environment is that it doesn't just create the rust on the surface of the metal, because rust has a very low density compared to the metal below. What it does is it expands. And when it does that, it flakes, right? You look at an old car or an old tractor sitting out in the field for years, you'll see the metal on it has flakes coming off of it. That's because as the rust forms, it pushes the metal apart, right? It makes it, and it exposes new metal. So eventually that car, that tractor will just rust down to nothing. Nothing, it won't have anything left but the tires and the tubing. How do we prevent corrosion? Well, there are many ways that are being used to stop corrosion. One is just to cover it so water can't get to it, air can't get to it, right? Paint it. Or like we used to do with steel buckets, is galvanize them. Just take the steel bucket and dip it in molten zinc, cover it with zinc. Okay, that prevents oxygen and water from getting to the iron underneath. It also, because zinc is more active metal than iron, It also causes the zinc to corrode rather than the iron underneath. Or we can alloy it. Right? Probably the most famous alloy for prevention of corrosion is stainless steel. Stainless steel is an alloy of iron or steel, iron and carbon, and a more active metal like chromium. Right? There are various grades now of stainless steel, and they have different combinations of metals in them. But originally, the chromium was added at about 35%. And what happens was the chromium in the steel would corrode instantly. And its density of the oxide of chromium is about the same as the metal. So it just created a nice layer on the surface, so thin that it still shines. And if you scratch it, the reaction is just that quick, and it will seal the scratch. So we protect the iron with the more active metal. Cathodic protection is the way that steel tanks buried in the ground used to be protected, and pipelines, some pipelines still are protected. So we connect the metal with a more active metal, which becomes the anode. It's called the sacrificial anode. In this case, we're showing magnesium. Magnesium readily corrodes, and when it does, it's an anode, so it produces an electron stream through the connecting wire to the cathode, or the buried pipe or tank, and keeps it from corroding. You'll also see this on ships. Right? Ships will have a belt of zinc strapped to the sides of the ship, usually below the waterline. And in salt water, the zinc will corrode instead of the iron of the ship, and provide electron stream into the iron of the ship and keep it from corroding. Now that's when the engines are shut off, when there's no electricity. If there's electricity, then we can provide a trickle of electrons into the hull of the ship, and then the zinc and the iron both will not corrode. So usually you don't have to replace the zinc unless the ship sits for years in salt water, and then you might have to replace the zinc electrodes. Okay. Which part is the cathode? The buried pipe, of course. Okay, now electrolysis. I think this is the last one. Electrolysis is the reverse process, where we convert electrical energy into chemical. So in effect, what we're doing is we're deriving a spontaneous reaction in reverse by exceeding its spontaneous voltage. So if the process gives us, say, 1.5 volts in the spontaneous direction, all we have to do is apply voltage in the opposite direction a little bit more, 1.51 volts, and that'll drive the reaction in reverse. So if we were to, in a fuel cell, we have hydrogen and oxygen producing a voltage. Instead, if we take water and we apply a voltage exceeding that into the water, we will split the water molecules into oxygen and hydrogen. That's electrolysis of water. And this is what can happen also in a lead acid battery if we overcharge it. Circuitry is built into the system so that when the battery is fully charged, we don't try to put more voltage into it. Because if you do put more voltage, you overcharge it and you start breaking down water molecules, producing hydrogen gas, and your battery can explode. So older batteries used to have caps on them, right? There would be 6 cells, separate cells, and we put those in series. Each cell is 2 volts, put them in series, and you get 12 volts. But at in each cell, we have a cap with a hole in it, a little vent. So if by some means we overcharge the battery and it produces hydrogen gas, it's got a place to escape. Now we have sealed lead acid batteries, and they have built into them chemistry that will scavenge hydrogen if it's produced. Let's see. Well, yeah, this is a hydrogen economy is the holy grail of mobile energy transfer. The other holy grail for energy is fusion power. So if we had both of them, then we would have a limitless supply of energy from here to eternity. Okay, there's a stoichiometry involved in electrolysis that we can use to calculate how much cathodic metal can be produced, right? At the cathode, we are taking ions, we are reducing them and making metal deposited on the electrode. So we can do that with things like car bumpers, right? Car bumpers used to be chromed. We would deposit chromium ions from solution onto the bumper as chromium metal, and we would use electrolysis to do it. Well, you can calculate how much chromium you can put on that bumper if you know two things. If you know, well, have to know the chemistry, right? The stoichiometry of the reaction. And then if you know the current, right? How many coulombs per second? How long? How much time? And then the stoichiometry of the equation, you can calculate how much chromium is deposited on the bumper. And that's what this illustration is trying to tell us. It'll make more sense if we do a calculation. Okay, so let's take this calculation. An unknown metal is electrolyzed. It took 52.8 seconds for a current of 2 amps to plate 0.0719 grams of the metal from a solution containing MnO3 to the third. What is the metal? All right, this takes it a little further, but we can do it. All right, so what's the stoichiometry? Well, we've got M is our metal in solution, right? What's the charge on that metal? Well, look, we have 3 nitrate ions. Each nitrate is a -1. So this metal has to be a +3. That means we need 3 electrons to produce the metal. Okay, that's the stoichiometry. Now, excuse me. We know the mass of the metal that's produced. So if we want to find out what metal this is, we need the molar mass. Right? We need mass per unit moles of the metal. We know the mass already, 0.0719 grams. We need to know how many moles of metal are deposited. Okay? So the way to get at that is to say, we need to know how many moles of electrons were transferred in this process. So if we say we have 52.8 seconds and 2 amps, right? 2 amps is equal to 2 coulombs per second. That's the current. How long did it last? 52.8 seconds. So 52.8 seconds gives us the number of coulombs. But we need to know the number of moles of electrons. So we need another conversion factor. Right? Got rid of these. Now we need to get coulombs and moles of electrons. So what's our conversion factor? Here. 96,485 coulombs. 96,485 coulombs for 1 mole of electrons. So now that gives us the moles of electrons. Right? Moles of electrons. So what's the ratio? Well, if we knew moles of electrons, for every 3 moles of electrons, we get 1 mole of metal. There you go. That's your whole equation. We got moles of metal. So I need a calculator. All right, we got 52.8 times that. 96,485 divided into it, and 3 divided into that. So that gives us 3.65 times 10 to the minus 4 moles of metal. So we calculate molar mass is mass, which is 0.0719, 0.0719 grams per mole. That's an expression for molar mass. 3.65 times 10 to the minus 4 moles. So 0.0719 and divide that into it. I get 197 grams per mole. Yep, 197. So we go to our periodic table. 197 is, the nearest thing to that is gold. Oh, there it is. I did it the hard way. But that's how you use stoichiometry and voltage and current to answer these questions. All right, one more. So if we have a solution that's composed of 0.1 molar of each one of these ions, lead, copper, lead 2 plus, copper 2 plus, tin 2 plus, nickel 2 plus, and zinc 2 plus. What order will these metals plate out as the voltage is brought up from 0? Increase the voltage gradually in the reverse direction, of course. So we're going to reduce these metals. So how do we determine that? Well, first, where do the metals form? The metals are going to form on the cathode. That's where they're going to be reduced. All right. That's the site of their reduction. The reduction potentials will predict the order of plating because they're occurring on the cathode. So the more positive the standard reduction potential, they plate out first as the voltage is increased. In other words, the higher the opposing voltage is required to drive reactions to reverse the E as it becomes more negative. So as we move down the chart, the reduction potential becomes more negative and requires more voltage to oppose it. So the ones that have the higher positive voltage as a reduction potential will plate out first. And since they're all at the same concentration, we don't have the issue of differences in concentration and Q values, and that can mess with our calculations. So here are the reduction potentials for each one of the metals. And as it turns out, they're all in the right order, right? Oops, sorry. Well, we put them in this order. The one that's going to plate out first is copper, then lead, then tin, nickel, and zinc. So the more active metal plates out last. So our activity series says zinc is more active than nickel, more active than tin, more active than lead, more active than copper. And The least active one is going to play it out first because it takes less voltage to oppose its reduction potential. All right. Commercial electrolytic processes, production of aluminum. Aluminum used to be, when it was first discovered, and back in the early 19th century, during the Emperor Napoleon the Third, I think it was, aluminum had to be produced by chemical means. That made it very expensive. In fact, it was more expensive than gold. So when Napoleon, not the one with his hand in his shirt, but his descendant, when he entertained international visitors, he would bring out the aluminum flatware because it was more expensive than gold and a reflection of his majesty. We can purify metals with electrolytic process. Why? That first slide says that if we bring the voltage up to a certain level only, then we can plate out a metal from a mixture of metals and leave the others behind. That's the way we purify copper to make copper wire. It has to be very pure, 99.999% pure copper in the wiring in your house. Okay, we can plate things out. We can plate metals on surfaces, like chromium on a bumper. Now, it's a little more complicated than that. First, you plate, let's see, what do you plate first? I think you plate copper on the bumper, the plain steel bumper. Then you plate nickel on that, and then you plate chromium on that. And we studied this earlier in the semester, where you have the closest packing models. Copper has a better affinity for iron than the other two, but nickel has an affinity for copper, and then chromium has an affinity for nickel. If you tried to plate chromium out on iron, it would just flake off. Electrolysis of sodium chloride. What does that do? It reverses the reaction. Now you get this solid, which was actually, in order to do this, it has to be liquid. You got to melt it. And then you can apply a reverse voltage and get sodium metal plus chlorine gas, right? Just by reversing the voltage. So we get chlorine gas, which can be made into bleach or almost any other thing. It's an industrial gas. And you can make drain cleaner, sodium hydroxide with sodium. Just combine it with water and you got sodium hydroxide. So this is how we make aluminum now using the Hall-Héroult process. Right? They determined how to do it independently about the same time, so they both get credit for it. So we electrolyze bauxite, aluminum oxide. Now, the problem is aluminum oxide has a very, very high melting point. It's over 2,000 degrees. So the trick was for Hall and the Frenchman, Héroult, to combine something with the aluminum oxide, alloy it. Actually, it's a mixture, not an alloy, so that the melting point would be reduced. So by adding this cryolite, we call it, which is sodium aluminum fluoride, the melting point was reduced by over 1,000 degrees, which now made the process economical. We need energy, but not as much as before. So the process takes place in solution. So the electrodes are graphite rods. And when the aluminum is reduced, it turns into metal and it just sinks to the bottom. Molten aluminum sinks to the bottom. And once the process reaches a certain point, all you have to do is knock that plug off the bottom and out comes the pure aluminum. And this process made it so much cheaper. And what you need is cheap electricity. So that's why aluminum processing plants are built on rivers where you have cheap hydroelectric plant, like Tennessee Valley project, or in coal country, like in Pennsylvania. That's where Reynolds Aluminum is located, where you can produce cheap electricity with coal because you need lots of it. You can electroplate spoons, right? If your spoon becomes corroded, right, and you have bona fide silverware, or you could have silver-plated silverware, you can restore the silver simply by an electrolytic process. And this last one is how we produce chlorine gas and sodium by electrolysis. And that's it. All she goes. And I went over a half hour, which is not unusual. Any questions? Ooh, it got moved around. I hope I forgot to lock the wheels. That's the problem. Okay, so Thursday, the review document I was going to give you was version 2. Well, I'm only going to work from version 2 in the review document to save you a little time and effort. So I would have handed out the PowerPoint slides, review document, work problems for version 2, and the crossword puzzle for chapter 18. And we'll do a review on Thursday and follow that up with the lab on formation constant of a complex ion. Okay. Well, let's see. That's it. All done.